Welcome to True Projects. In this video, we are going to explain about the project entitled as Traffic Crash Countermeasure Recommendations Using Deep Neural Networks, a decision support tool for traffic safety engineer. So before getting into the video, let me give you the brief description about the project. The title refers to a decision support system that uses deep neural networks to analyze traffic crash data and identify patterns linked to accidents. Based on these patterns, the modern recommendation effective traffic crash countermeasures such as road design improvements or safety policies. The tool is intended to help traffic safety engineers to make data driven, accurate, and timely safely decisions. Coming to the abstract, this abstract describes a decision support system that applies deep neural networks to analyze complex traffic crash data and predict high risk locations. By learning patterns from historical crashes, road conditions, traffic volume, and environmental factors, the system recommends targeted countermeasures for specific traffic scenarios. The goal is to support traffic safety engineers with data driven insights that help reduce accident frequency and improve overall road safety. Coming to the existing system, the existing traffic safety management system mainly depends on historical crash data, manual evaluation, and expert judgment to select appropriate countermeasures. It commonly uses traditional statistical approaches or basic machine learning models, which struggles to capture complex and nonlinear relationships in large traffic data sets. This process is often time consuming and subjective, relying heavy on experience of traffic engineers and may fail to detect subtle crash patterns, resulting in less precise or generalized safety recommendations. Coming to the proposed system or base paper work, the proposed system uses a deep neural network based approach to improve traffic safety decision making by analyzing large and diverse traffic and crash data sets. It processes information such as road geometry, traffic flow, weather conditions, and past accident patterns to predict crash prone locations and recommended subtle countermeasures. By presenting these insights through a user friendly decision support interface, the system helps traffic safety engineers prioritize effective interventions while improving accuracy, reducing human bias, and enabling scaling data driven safety improvements. Coming to the dataset, the traffic crash detection dataset is a structured collection of historical traffic accident data intent for analyzing crash patterns and supporting machine learning based safety prediction models. It typically includes features such as crash location, time and date, environmental condition, and road characteristics that influence crash occurrence and severity. These multidimensional attributes make the dataset suitable for training deep learning and machine learning models to access risk, detect high crash patterns, and support data driven decision making in traffic safety engineering. Coming to the novelty or extension or enhancement or improvement. An ensemble model was developed by combining decision tree, random forest, and CNN plus LSTM algorithms. This approach leverages the strengths of multiple models to improve prediction accuracy, robustness, and reliability compared to using a single model. Next, Lime and SHAP were integrated to interpret the model's prediction by highlighting the most influential features. These techniques helps user understand how different factor contributes to crash risk, increasing transparency and trust in the system. Along with that, a Flask framework was used to build an interactive web interface where users can input traffic related data. The trained models process this input and provide real time predictions, making the system accessible and practical for traffic safety engineers. Coming to the flow of the work, first we need to import the packages. Required Python libraries for data handling, visualization, machine learning, deep learning, and explainability are imported to support the entire workflow. Next, exploring the dataset. The traffic crash dataset is analyzed to understand its structure, features, target labels, and overall data distribution. Next, data pre-processing. Null values are removed to ensure data quality and avoid errors during training. Duplicate records are eliminated to prevent bias and redundancy in the dataset. Next, label encoding. Categorical variables are converted into numerical form using the label encoder, making them suitable for machine learning models. Next, normalization. Feature values are scaled using standard scalar to maintain uniformity and improve model convergence, especially for deep learning models. Next, data visualization. Label distribution is visualized to understand class balance. Correlation metrics is generated to identify relationship between features and reduce redundancy. Next, building classification models. Multiple models are developed and evaluated including random forest, light GBM, ensemble model, deep neural network, convolution neural network, hybrid CNN plus LSTM model for capturing spatial and temporal patterns. Next, training the model. Each model is trained using pre-processed data to learn crash patterns and make accurate predictions. Next, model evaluation and comparison. Models are compared using performance metrics such as accuracy, precision, recall, and F1 score to identify the best performing approach. Next, performance visualization. Comparison graphs are generated to visualize, analyze, and compare the performance of all the models. Next, save the best model. The model with the highest performance is saved for deployment and future prediction. Next, explainable AI visualizations. Line explains individual predictions by highlighting influential features. SHAP provides global feature importance to understand overall model behavior. Coming to the front end, a user interface is developed using Flask framework, including user registration and login functionalities supported by an SQLite database. The front end allows users to enter feature values required for traffic crash prediction. User provided inputs are pre processed using the same techniques applied during model training to ensure consistency. The saved best performing model is used to generate predictions based on the user input. The final prediction results are displayed through the front end in a clear and user friendly manner, supporting practical decision making for traffic safety engineers. The algorithms used in the project are random forest, light GBM, ensemble, DNN, CNN, CNN plus LSTM. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consisting of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consist of application framework Anaconda, primary language Python, front-end framework Flask, backend is Jupyter Notebook, database SQLite 3. Technologies which we use to build the front end are HTML, CSS, JavaScript, and Bootstrap 4. To execute the project first, we need to open the code folder which contains project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. Models. These are the model file which contain the algorithm information which will be loaded into the project code during the runtime. Notebook.ipynb file. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Now, coming to the execution of the project. Firstly, you need to copy the path of the code folder from the address bar of the file explorer. Then, open Anaconda prompt. Use the command cd followed by a space and paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link which is provided by the Flask framework and paste it in any web browser. I prefer Chrome. The home page of the project should now be displayed in the browser. This is a front end built using Flask framework. In this page, we have home button, login button, and create an account button. Firstly, click on create an account button so that the sign up and explore form will be open where you need to enter the details and create an account for user authentication like username, full name, mail ID, contact number, and a strong password. Then click on sign up so that all the given details are stored in signup.db and the login HTML will be open where you need to access the application with the help of username and password. Then click on login so that the prediction page has been displayed. In this page, we have prediction button, graphs button, notebook button, and logout button. Firstly, click on prediction button so that the crash category prediction form will be open where you need to select the parameters to predict the crash model from CM0 to CM5. So we have the parameters like additional information, road facilities A, road facilities B, road facilities C, vehicle type A, and vehicle type B. Let us give the input. After entering the input, let us click on predict crash model. So the given inputs are pre-processed and the output will be displayed for the given inputs are CM5. The predicted crash model is CM5. Here we have the inputs which we are given and we have the main objective like general traffic safety management and analysis. We also have the selected subject objectives and then click on analyze another so that the form will be open again. Now let us give another attributes and check. After giving another input, let us click on predict crash model so that the given input is pre-processed and the output is displayed as CM3. The predicted crash model is CM3. The input parameters are given below. The main objective like car to car or single car crash prevention and mitigation. We also have the selected subject objectives. And again click on analyze other so that the form will be open again where you can enter the details and predict the output. Now click on graphs so that the graphical representation of the projects will be displayed. Now let us check one by one. First we have sample outcome graph. The bar chart shows the count of 6 labels. All bars are the same height indicating each label has the equal count of above 5000. This suggests the data is evenly distributed across all categories. Next, we have sample outcome graph. This heat map shows the correlation between the label and different road facilities and vehicle type features. Most correlations are weak, indicating limited linear relationships among variables. The label has a moderate negative correlations with road facilities B and vehicle type A. Overall, strong correlations are present, suggesting features are mostly independent. Next, we have confusion matrix ensemble graph. This confusion matrix shows the performance of an ensemble model across 6 classes. Most predictions fall on the diagonal, indicating high classification accuracy for each class. Some confusion occurs mainly between class 2 and 4 and between class 0 and 3 by 5. Overall, the model performs well with only limited misclassifications. Next, we have accuracy graph. The bar chart compares the accuracy of different machine learning models, DNN, Ensemble, Light GBM, and CNN plus LSTM achieves the highest accuracy around 93 to 94%, showing strong performance. Random forest performs slightly lower but still competitive. CNN has the lowest accuracy among the models, though it remains close to 90%. Next, we have F1 score graph. The graph shows the macro F1 score of different machine learning models reflecting their balanced performance across classes. DNN, LSTM, and LightGBM achieve the highest F1 scores around 92 to 93%, indicating strong and consistent classification. Random forest performs slightly lower, but it remains competitive. CNN has the lowest F1 score, suggesting weaker performance on minority or harder classes. Next, we have recall graph. The bar chart compares the recall scores of different machine learning models, showing how well they identify actual positive cases. Ensemble, DNN, and LightGBM achieve the highest recall, indicating strong sensitivity. Random forest performance slightly lower, but still reliable. CNN has the lowest recall, meaning it misses more positive instance compared to the other models. Next, we have precision graph. The bar chart compares precision across different machine learning models. Most models perform similarity with precision values clustered around 90 to 94%. DNN and ensemble models show the highest precision, while CNN has the lowest among the group. Overall, all models demonstrate strong precision with only minority difference between them. Next, we have line explanation graph. This line plot explains which features influence a single model prediction and by how much. Features with bar to the right increases the prediction, while those to the left decrease it. Road facilities A has the strongest positive impact, where vehicle type A has the strongest negative impact. Overall, the graph highlights the most influential features driving the specific decision. Next, we have Sharp value graph. The Sharp summary plot shows how each feature impacts the model prediction across all samples. Features at the top have the strongest influence on the output. Points to the right increases the prediction, while points to the left decrease it. With color indicating low, blue, to high, it's red. Feature values. Overall, vehicle types contribute more to predict changes than road facility features. Finally, we have a sample outcome graph. This graph shows how different features push the model's prediction away from the baseline. Starting from the average prediction, vehicle type A increases the output the most, while vehicle type B decreases it. Additional information slightly raises the prediction, and road facilities have minimal impact overall. All contributes combine to reach the final prediction. Then click on Log Out. So finally, the project demonstrate a data-driven approach using deep neural networks to predict high-risk traffic locations and recommended effective safety countermeasures. By integrating explainable AI and a user-friendly interface, it enables traffic safety engineering to make informed, accurate, and timely decisions. Overall, the system enhances road safety, reduces accident, and provides a scalable solution for proactive traffic management. This is all about your project. Thank you.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.